My name is Frederico. I'm here with Jose and Felipe Marques. For our poster, we are conducting an empirical study on applying program analysis and testing tools to student code. In the majority of computer science courses, students are required to implement code projects where they will inevitably introduce software bugs. However, there is a variety of tools specifically designed to find this common type of bugs. We want to measure how well these tools perform in this task according to metrics of precision, recall, and resource usage, such as memory and time consumption. Ultimately, we want to make a case for the introduction of testing and verification tools in undergraduate courses. To conduct these experiments, we created a curated data set consisting of 1,160 student projects annotated with known bug locations. For these bugs, we consider stack and heap overflows, invalid pointers, uninitialized memory, stack underflows, and memory leaks. We plan on evaluating 9 state-of-the-art testing and verification tools on these datasets, in particular FuseBMC, Lead Cluster, Verifuzz, KLEE, Symbolic, CPA Checker, inferring tools. We already have some preliminary results, in particular for Infer, Pulse, KLEE, and Symbiotic. Our methodology, as shown in this diagram, is divided in 4 main steps. First, we use an annotator that consists in program-specific input generators in conjunction with address sanitizer to obtain a collection of bugs that we consider the ground truth, which will compare the verification tools with these. In step 2, this annotated dataset is parsed by an instrumenter that removes possibly problematic Libc functions, specifically for symbolic execution tools, and replaces it with a common API that all tools can understand. After executing all the verification tools, we confirm that the reported bugs are in fact bugs and not false positives. If new bugs are found, we add it to the collection, to the annotated dataset, and consider and additional and add it to the ground truth. We selected the 9 tools according to the following criteria. We selected the 5 best performing tools in the cover area category in TestCom 22, the winners of categories Mem Safety, No Overflows, and Software Systems from SCCom 22, and we also decided to include other high-profile static analysis tools, in particular Infer tools. Additionally, if you want us to include our tool, please contact us, come talk to us near the poster. We'll be more than happy to include it. The preliminary results are summarized in this table, where you can see the total number of bugs uncovered by each tool for each project, and as well as the average. We determined that all tools are performing relatively well and covering most of the bugs with high recall and precision, but these are still preliminary results. We already have more updated results in the poster, so you can check that out. Finally, we encourage you to collaborate with us. We'll try to make sure that the data set is open source. We are also talking with the university. This is student code. And once again, if you would like us to include our tool, we'll be more than happy to do it. Please come to talk to us, and that's it.